these, you have them written down somewhere, you have an easy access to it so you can keep studying this over and over. But these are my geometric, and these are my arithmetic forms. All right, we're going to start off. So today's basically counting things, counting how many things I have, counting how many possibilities I have, counting how many outcomes there are, so on, so forth, and what have you. All right, so the first one says, consider it 6 a.m. You are groggy and you have to pick out an outfit to wear. Lucky for you, you didn't do laundry and you actually, it says you have 3 pairs, but we're going to say only 2 of them are clean still. We're going to change that to a 2 just to make this a little shorter. So we're going to say you only have 2 pairs of pants and you have 3 shirts to choose from. That's it. That's pretty easy. And we're going to assume that all shirts match all the pants so we don't have to worry about that. How many outfits can you possibly wear? So what we're going to do is we're going to draw something called the tree diagram. The tree diagram really is something that's going to be like last case, a last resort of sorts. If you're just like, I can't quite figure out what I'm doing with these numbers, we can draw a tree diagram, or most likely we can just see it in our head. So we're going to start with you. That is you getting up in the morning. Now, we're going to pick the pants first. So choosing your pants, you have 2 possible pant choices. You can choose either pants number 1 or pants number 2. This is 1 again. Let's change it to a 2. All right. Let's say we chose our pants number 1. Let's say we chose some jeans. So I have jeans and I have khakis to choose from. So I chose pants number 1. Well, once I choose my pants, I now have 3 shirts I got to choose from. So we'll say pants number 1, you can choose shirt number 1. You could choose just shirt number 2. Or you can choose shirt number 3. Well, maybe I didn't choose pants number 1. Maybe I chose pants number 2, in which case I have my khakis on, but I still have to choose a shirt to wear. So once again, if I chose pants number 2, I could choose shirt number 1. I could choose shirt and number 2, and I can choose shirt number 3. That was supposed to be a 3. So each choice leads to our whole outfit. So pants number 1 could go to 1, 2, 3 possibilities. And we have pants number 2 can go to 3 possibilities as well. So in total, we have 6 possible choices. So it says how many outfits could you wear? That is 6 outfits. Each pair of pants leads to 3 shirts. 3 shirts times the 2 would give me my 6 outfits. Well, an easier way to do this problem, rather than having to draw all of this stuff, is we could just say, notice that each choice of pants leads to 3 choices of shirts. In other words, if I have 2 pairs of pants, so 2 choices for pants, and 3 choices for shirts, we can just do 2 times 3 equals our 6, also our 6 outfits as well. What that is, the pants times the shirt, is called the fundamental theorem, or the fundamental counting theorem. So it's called the fundamental counting theorem. Which is, if you can choose one item from a group M, which we had pants, and we had to choose a second item from group N items, that was our shirts, then the total number of 2 item choices is M times N. But it is not relegated to just 2 groups. You can have unlimited number of groups that you might have to multiply over and over and over. And in fact, this bottom example is one of those that we have more than just 2 different possibilities. So down below, we're picking a phone number. And a phone number consists of 10 digits, minus that 1 that goes way in front to say it's the United States. We're going to skip that one. We're going to start with our area code. So the first three are area code. However, an area code cannot start with a 1 or a 0, and that's 100% true. There are no area codes that start with a 1 or a 0. Next, we're going to have 7 digits, which are called your local telephone number, which cannot start with a 0. Also true. There's also a lot more limitations on phone numbers. Surprisingly, there's more than you think. One of the bigger ones is you cannot have a combination of 911 in your phone number. So you couldn't be like 682-9113, because in theory, it would actually call 911. I have not tried it. I don't highly suggest you try it to see if it works or not. Yes?
One time I saw a thing online. It was like say the words 9/11 to Siri, and then it'll be crazy. It was gonna be some like conspiracy theory thing.
Yeah.
And I said it, and then I called the cops, and they came. I was like, yeah, sorry,
I was trying to do a conspiracy thing.
I thought it was gonna be like, yeah. It was embarrassing.
And it turns out once you call 911, they call you back if you hang up right away or anything. They have to come if you don't answer, yeah. So I'd avoid doing it because you either have to talk to someone from 911 or they're going to show up at your house. I just wanted to see if it would actually, there you go. That'd be, it's always good when cops show up to a school. Looking for you. All right, anyway, we're going to come up with how many possibilities there are to make a phone number based upon just these few limitations. There are more, but this will just make it easier. So we have a phone number composed of 10 digits. Let's just do all 10 digits, but we'll do them as spaces. So we'll do 1, 2, 3, dash, 4, 5, 6, dash, 7, 8. I should make my dashes a little bigger. 8, 9, 10. All right. That is our phone number. It is like 414, whatever.
813.
813. There you go.
6221.
Okay. So I'm going to list all my possibilities. So we're going to start with our very first number of our area code. Well, an area code cannot start with a 1 or a 0. So how many possible numbers are there to be in this first spot? If it can't be a 1 or it can't be a 0. Yeah. There's 8 possible numbers. So it can't be a 0, it can't be a 1, but it can be a 2, 3, 4, 5, 6, 7, 8, 9. It can't be a 10, turns out. You can't put a 10 in one digit. So there's 8 possibilities. I highly suggest you count things with fingers if you're not 100% certain how many there are. Well, after that, the next 2 can be any number you want. So they can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 10 possibilities for the next one. So we're just listing all of our possibilities. For each number. All right, now we get to our local number. The only requirement is that a local number cannot start with a 0. So how many possibilities do I have for that first number of my local? I have 9. Yep. There are no constraints on any of the other ones, so those are all 10 as well. Well, now this is the exact example of what we have up here. It is our fundamental counting. I am picking one item from this 8. I'm picking one item from this 10, 10, 9, 10, 10, 10, 10, 10, 10. So it fits this. I'm choosing one option from each group. So to solve this problem, all I have to do is do 8 times 10 times 10 times 9 times 10 times 10 times 10 times 10 times 10 times 10, and you will get your total possibilities. So we're just going to use our fundamental counting theorem to say, well, possibilities are just going to be 8 times 10 times 10 times 9 times 10 times 10 times 10 times 10 times 10 times 10. Whew. That is a beast. That is a beast. What's my answer to this one? Hint. Well, not really a hint. You don't need your calculator for this one.
Can't you just do 81 times 10 to the
I probably wouldn't do that. I would just do 8, because, or it doesn't matter, right? If multiplication. I could throw this 9 out here and I can do 9 times 8. Well, 9 times 8 is going to be 72. Then we're just going to move our decimal place. 1, 2, 3, 4, 5, 6, 7, 8 places. So what's it going to come out to, Liam?
720 million.
I believe it's 7 billion.
Oh, 720 billion. Or
7,200 million. Yeah, it should be 7 billion 200 million. You would think so, but guess how many numbers there are actually. Think of how many phone numbers people have. Like a lot of people have like a cell phone, a home phone, a work phone. So if you think like everyone has 3 phone numbers at least, and think of all the numbers that are like you can't use. Think of all the numbers that are just not in circulation right now because it might be a person that doesn't have a phone anymore, but it still hasn't. There are thoughts that not that far away, we're just going to run out of phone numbers.
There's 4 digits on a license plate now.
Yep, same thing with phone numbers. They're thinking that possibly if they ever run out of numbers, they'll just add another local digit. So instead of 3, it might be 4. Or they might add an extra area code number, so you have 4 of those. Because just adding one extra digit would put another 0 after this, which would bump it up to 70 billion, which would make a lot more. That's just adding one extra digit, would add a 0 onto the end of this, which would make it 70 billion. Leon?
How would you subtract the possible areas where there could be a 911?
Yeah, because that's what I was thinking too. Is
Yeah.
if you
That's what
add it up,
we're not going to do.
We should do it. Wouldn't it just be everywhere there could be like 1 and then 2? And
Yeah,
3,
so you'd have to subtract
like 6.
basically 1 from here,
Yeah.
1 from here, 1 from here, 1 from here, 1 from here, 1 from here. So it wouldn't be that bad, but there's a lot more requirements on that as well.
wait, would it work still if you did it between like the dash with the second set of
Yes.
3 after the arrow?
Yeah. Because if at any point you dial 911, so let's say this is 92911. Now you have 911. All right, let's move on. Let's move on to permutations, because what that was actually a permutation. Very hard to calculate permutation using this form, but it is a permutation nonetheless. So let's say you're giving a speech, and you thought the best way to start a speech off was to tell 4 jokes back to back to back that have nothing to do with the other jokes. A, you're going to have a terrible speech, but B, you're wondering how many different ways you can tell these jokes. So I need to tell each of these jokes in a particular order. But I'm not going to tell the same joke over and over and over 4 times. So as soon as I use a joke, I have to throw it away because I already told that joke. So we're going to figure out how many different ways there are to tell each of these jokes. So let's go ahead and list them. Well, we have to do a first joke. Then I have to come up with what my second joke is going to be. Then I have to come up with my third joke. And finally, I have to tell my last joke, which would be my 4th joke. How many choices do I have to tell a first joke?
4.
I have 4 choices. I could choose any one of those 4. Doesn't matter. They're all just as funny. They aren't, but in theory, they're all just as funny. So I have 4 possibilities to tell my first joke. Do I still have 4 possibilities to tell my second joke? No, I am down to 3 possible jokes. Because I have 3 to choose from. So let's say I chose the Bill Murray one first. Now I have 3 to choose from. Well, now I chose maybe this one. Now I'm down to 2 jokes to pick from. And my 4th joke, well, I'm just stuck with it. I already narrowed it down to my 4th joke, so I only have 1 possibility. Well, this is, in fact, using our fundamental counting. I could choose 1 from 4, 1 from 3, 1 from 2, 1 from 1. So we can just go ahead and multiply all these together to come up with that there are 24 different ways to tell those 4 jokes. We have 24 ways to tell those jokes. This is an example of something called a permutation. This is an example of something called a permutation. So down below, it says A. Guess what? It's a permutation. I said it like 3 times, and it's right on top of the header. A permutation is an ordered arrangement of items that occur when. It's got to meet these requirements. No item is used more than once. No item is used more than once. For my example, each joke was only used once. Here is the bigger one to pay attention to, because tomorrow we're going to talk about combinations, which, if you remember, combinations and permutations are very closely linked. You have to decide which one to use when. For permutations, you're going to know to use a permutation because the order matters. The order of the arrangement makes a difference. That first joke has to be told first. I can't say, well, the first joke, I don't care if I say it the second. As soon as I pick as my first joke, it is stuck there. The order matters that I'm telling it first. Order definitely matters with these. So a permutation of n things. So think of your n value as your total things you can choose from. All right, think of it as like if you have a bag of candy, I'm going to choose 4 of them out of there. And that's a bad example because order doesn't matter. But think of your jokes. We had 4 possible jokes. So my n would be the number of jokes I can possibly choose from. This r is how many of them I'm going to pick. So let's say I had all 4 of the jokes, but I was only going to tell 3 of them. In that case, my n would be 4, because I had 4 total jokes, but I'd only choose 3 of them to tell. That'd be a 4, pick 3 of them. And the notation for that is p in parentheses n, comma r, where n comes first. Your n is always going to be bigger or equal to your r. Think about that. If I had 4 jokes and I had to choose 5 of them, that wouldn't make it, you should be like, that doesn't make any sense. That's the exact same thing that would happen if your r was bigger than your n. Your n is always bigger than or equal to your r, always. So if you're confused which one is your n and which one's your r, you can always default to whichever one's bigger. If they're the same number, who cares? You picked it right either way. All right, to actually plug this in, you're going to do n factorial over n minus r factorial. All right, let's do 2 examples. So the first one, you're coaching a baseball team and you have 13 players. You need to choose a batting order of 9 players. Guess what? The order matters, because if I put Mike in that first spot of batting and all of a sudden Charlie jumps up and jumps in front of him, he's going to be mad because he's supposed to be the first one. So order matters because you care where you're put, and it matters where you're going to go. So order definitely matters, and we're going to use a permutation where n is going to be our total pool of things to pull from. So that would be 13 players. Well, my n is 13. My r is how many I'm going to choose from those 13 players. Well, I'm going to choose 9 of them to be in my batting order. So that is 13, pick 9. In other words, we'll write it like this. Permutation of 13, pick 9. Well, plugging that in the formula, we're going to have 13 factorial over 13 minus 9 factorial, which is going to equal 13 factorial over 4 factorial. This is probably going to be something you're going to need to use your calculator for. Because if I try to eliminate this, if I try to eliminate it by hand, it's going to be kind of a waste of time. Let me show you real quick why it'd be kind of a waste of time. Because I could do 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. The only thing that would cross out is that 4 factorial and that 4 factorial. That's kind of a waste of time. I would not make you do this one by hand. So in this case, that wouldn't be efficient. So we're going to pull out our calculator. And guess what? We are not going to type in 13 times 12 times 11 times 10. We are not going to do that. You have a factorial button on your calculator. It's just buried in your math button. So you're going to go ahead and just click on your math button right there. So I clicked on my math button. You're going to see this PRB button that stands for probability. It has everything to do with probability. So I'm going to go to probability, and if you go down to 4, that is my exclamation point. So my exact example is going to be 13 factorial divided by 4 factorial. So let me quit and clear that. So I'm just going to type in a 13. I'm going to go to my math. I'm going to go to probability. I'm going to hit number 4, so it selects it for me. 13 factorial divided by 4. Do the exact same thing. Factorial. And hit enter, and that's going to equal a big old number. But that is our correct answer. So we're going to have 259,459,200 different ways to create that order. That's a lot to choose from. There's a lot on the plate, yeah. Oh, yeah. Well, think about this real quick. If this is how many ways there are just to pick 9 players for the 13, imagine what the chances are of winning the lottery when they have way more numbers. All right, next one. If 4 officers are to be elected from a group of 12 and no person can hold more than 1 office, how many different outcomes exist? Order matters for this. Order matters, and I want to show you exactly why order matters. So I'm going to put order matters. And why it matters is because, consider this, we have 4 officers to be elected. So maybe you need to have a president. Maybe you need a vice president. Maybe you need a treasurer. Maybe you need a secretary. Do you care which one of those you get picked as?
Yeah.
If you're running for president and like, well, you didn't get it, but you got secretary, or you're like, yes, that's just the same. No. Order matters because you care about what position you get in. If I said there was 4 secretary positions open, then you'd be like, okay, it doesn't matter if I was secretary number 1, number 2, number 3, number 4. Then it wouldn't matter. But if you care, that's generally when order matters. If they mess it up, the order, and it's bad, that's when order really matters. So order matters for this one. What I want you to do is go ahead and solve this one. If you haven't already, go ahead and solve this one. In theory, you would have did P is 12, pick 4 of those, which is going to be 12 factorial over 12 minus 4 factorial, which would be 12 factorial over 8 factorial, and you come up with 11,880. Good, bad, somewhere in between? It should be kind of a step back today, because we're just dealing with permutations, so you pretty much know the whole homework permutation. You don't have to decide if it's permutation or a combination. So let's go ahead.